Hello and welcome to this presentation on activating and deactivating loads when using Ansys Workbench Mechanical. Here is a 3D solid model. It has been meshed with 3D solid elements. These are high order elements so that they have bending properties that will be sufficient for our work. This is a model with 3 load steps. You could see it right here. The loads on this model include a pressure on the top face, a fixed support along this edge, a displacement support on this edge in which we can set 0 or non-zero values for x, y, and z, and a force down on the vertex here on the left and the vertex here on the right. If we go look at these loads, the fixed support exists through all load steps. There's no option for turning it on and off, for activating it and deactivating it. The other loads, however, can be activated and deactivated. Here's the pressure on the top face. In the tabular data down here on the lower right, notice that in the first load step we ramp the pressure up from 0 to a value of 0.04. We maintain it at that level through the second load step, and then we don't reduce it to 0. What we do is deactivate it for the third load step. In order to deactivate a load, click on the row, right-click, and choose Activate or Deactivate at this step. You could do this for multiple rows at the same time. It toggles the value between Activate and Deactivate. Because the load was deactivated, you can see that it was grayed out, and that's your tip-off that the load has been deactivated at that load step. Let's go look at the force. That we're leaving deactivated for the first 3 load steps. That's really no different from just leaving it at 0, but we've done it for the point of illustration. That's because it's active in the third load step. And what you'll discover is that the load in fact gets ramped up to a value of 20. Let's now look at the displacement. Here's the displacement on this left edge. You can see it in yellow. And it has been deactivated in load steps 2 and 3. But something interesting happens. That displacement support, which holds the y value at 0 through the first load step, doesn't just disappear instantly in the second load step if you take substeps. Ansys does something interesting internally, and for that, let's go look at the displacement delete command. Workbench jobs are run by the full Ansys package in the background, and the full Ansys package is fed a sequence of Ansys commands that execute the entire model. Here's the displacement delete command. It removes a degree of freedom constraint. You indicate the node, you indicate what degree of freedom. You have the option to indicate other nodes in sequence. Now there's an argument here at the end, this R key. Now, loads are step removed if you just put in the delete command. But in Workbench, they use a non-default setting for this deletion. They, in effect, ramp the support off, but they don't ramp it to 0. What they do is they back off the reaction forces, if you read this. And let's go look in more detail. They ramp down the reaction forces if you take substeps, so that the structure gradually moves to the condition it would be in if there was no displacement constraint happening there. And we'll see this in the model that I'm going to show you because I did go through substeps. Let me go back. There's the delete command, and you can see that extra argument. Here are some lines taken from the ds.dat file that runs the Ansys model. These are commands to the full Ansys package. In here you can see that I executed my second substep. You can see time comma 2 through 10 substeps. Here's the delete command that removes that Y displacement constraint from that group of nodes. And they used that extra argument for force that requests that the reaction forces be ramped from the full reaction force at the beginning of the load step to 0 at the end. Now let's go see the behavior of the model. I've solved this model. Here's the deflection at the end of the first load step. You can see that the pressure on the top has made the structure move down. It's fixed along this edge and prevented from movement in Y along this edge. And you can see that the displacement ramps up linearly because it's a small displacement linear model. In the second load step, we're not seeing any big change in the amount of deflection, but there is something happening. What's happening on this edge? The constraint on vertical movement is being backed off gradually through these substeps. Let me run it as an animation. I'm going to animate through the results, not by linear interpolation. And let me run that animation over 10 seconds. Now watch what happens. We put the pressure on and the structure moves down. Then we release the displacement constraint on the left edge right now, but we do it gradually. Now they're not turning zero displacements into specified amounts of displacement. What they're doing is removing the displacements but gradually backing off the restraint force as we go through these substeps up to the end of the second load step. Now look at this sudden change in displacement. What's happening is in the third load step the pressure is being removed instantaneously. And that's why we get this sudden drop. Then these forces right here, one on this vertex and one up here, are being turned on. Now they're turned on from a deactivated state, but they are in fact ramping up. And you see the fact that that force is ramped up as we go from what would have been 0 here to some value. Let me run the entire animation now. Pressure on the top and the left edge prevented from moving. Then it's released on the left edge. Then the pressure's suddenly turned off and the forces are ramped up. Users can take advantage of this, but they also have to be very aware that a specified displacement that could be 0 or non-zero can be deactivated. But in the load step where it's first deactivated, if you are taking substeps, such as I've taken here, I've taken 10 substeps in every load step, then that displacement, although the displacement constraint is turned off, reaction forces exist until the end of the load step, and you'll get this gradual release of what's happening on the left edge. I'll run the animation one more time. It's not released. They're backing off. And then we get a complete change with the pressure disappeared and forces ramping up. If you were running a transient analysis, this was just static. If you were running a transient analysis and you want a displacement constraint like this to disappear, in the transient run, you'll want this time interval for the load step where you deactivate it. You'll want this time step to be a very small time step in real time in a transient if you want it to disappear very quickly. Thank you for joining me.